Out there, in the absolute and unforgiving blackness, time itself behaves differently. The void between galaxies is a tapestry woven from distance and the constant, unrelenting speed of light. To look out into this expanse is not merely to look across space, it is to look backward into the deepest corridors of history, to an epoch so remote it defies human comprehension. For 13 billion years, light from the universe's infancy has been journeying, its waves stretched and fatigued by the expansion of space-time itself. This ancient, weary light carries a story, the genesis of everything we see. And now, for the first time, we have built an eye capable of reading its faint, whispered script. 1 million miles from Earth, a golden honeycomb drifts in the silent dark, shielded from the glare of its own home star. This is the James Webb Space Telescope, humanity's most ambitious sentinel, an infrared oracle designed for a single profound purpose: to witness the cosmic dawn. Its 18 hexagonal mirrors, coated in a gossamer layer of gold, work in perfect unison, a colossal bucket designed to catch the faintest, oldest photons in existence. For months, it has been staring into a patch of sky that appears utterly vacant to the naked eye, a region of profound emptiness. But Webb sees differently. It perceives the universe in wavelengths of light invisible to us, the very colors of creation. In the quiet hum of a data processing center back on Earth, a team of astronomers watched as the first images from a new deep field survey were stitched together. They were looking for the faintest, reddest smudges imaginable. These would be the seeds of today's majestic galaxies, the first chaotic nurseries of stars, igniting in the primordial gloom. One by one, the candidates appeared, faint and small, just as theory predicted. But then, something else materialized from the digital noise. An object designated with the unassuming catalogue number, 25P Nu 39. It was a smudge like the others, but it was different. It was too bright. It was too clear. And as the spectral data began to stream in, a quiet disbelief rippled through the control room. This was not some faint, embryonic proto-galaxy. The light from 25P Nu 39 told a story that was, by all accounts, impossible. It was a ghost from a time when such beings were not meant to exist. The data suggested a galactic metropolis, a sprawling city of stars, shining in the universe when it was a mere toddler, less than 300 million years old. This is the equivalent of finding a fully formed, functioning skyscraper in the archaeological strata of the Stone Age. It was an anomaly, a paradox written in starlight, a discovery that didn't just add a new chapter to our cosmic history books, but threatened to tear the entire volume to shreds. The impossible galaxy, 25P Nu 39, had just been discovered, and with its silent, ancient light, it brought a crisis to the very heart of cosmology. To truly grasp the magnitude of this confounding discovery, we must first appreciate the revolutionary instrument that made it. The James Webb Space Telescope is not merely an upgrade to its predecessor, the venerable Hubble. It represents a fundamental shift in our ability to perceive reality. Hubble, a legend in its own right, gave us our first crystal-clear views of the cosmos, but it was primarily an eye for visible light, the same narrow spectrum our own biology evolved to see. It was like trying to understand the full richness of a symphony by only listening to the violins. Hubble could see the grand, mature galaxies, but the universe's earliest moments, its opening chords, were shrouded from its view. The genesis of the cosmos is a story told in infrared. Imagine standing on a harbor, watching a ship sail away toward the horizon. As it recedes, its details fade, and its colors seem to wash out. Now, imagine the universe itself is the expanding ocean. A galaxy born in the early cosmos emits brilliant, blue-white light from its first massive stars. But as that light travels for billions of years across an ever-stretching fabric of space-time, its waves are pulled, elongated, and shifted, much like the sound of a receding ambulance siren drops in pitch. This cosmological redshift pushes the brilliant, high-energy light into the lower energy, longer wavelengths of the infrared spectrum. The cosmic dawn is forever invisible to human eyes. To see it, we needed to build an eye that could perceive this cosmic heat signature. Building such an observatory was one of the greatest engineering challenges humanity has ever undertaken. Its primary mirror, over 21 feet across, was too large to fit into any existing rocket. So, it was designed like a piece of intricate origami, a golden flower that would have to unfold itself flawlessly in the vacuum of space, a million miles from any helping hand. Each of its 18 beryllium segments, chosen for its lightness and stability at extreme cold, had to be polished to a precision measured in atoms and aligned with nanometer accuracy. If this mirror is the telescope's eye, its sunshield is its very soul. A 5-layered, kite-shaped membrane the size of a tennis court, it is an extraordinary feat of thermal engineering. It separates the observatory into a hot side, facing the sun, and a cold, dark side, where the scientific instruments reside. The temperature difference it maintains is staggering, from a scorching 85 degrees Celsius on the sun-facing layer to a mind-numbing minus 233 degrees on the instrument side. This extreme cold is not a luxury, it is an absolute necessity. Webb is so sensitive to infrared that its own heat would blind it, drowning out the faint whispers from the dawn of time. This marvel of engineering was then launched and sent on a month-long journey to its final destination, the second Lagrange point, or L2. This is a special, gravitationally stable location in space, a cosmic parking spot where the gravitational pulls of the Sun and the Earth balance perfectly. Here, Webb can orbit the Sun in lockstep with the Earth, keeping its vital sunshield always pointed at the Sun, Earth, and Moon, ensuring its delicate instruments remain in perpetual, frigid shadow. It is from this lonely, silent outpost that the Golden Sentinel began its work, turning its gaze toward a tiny, dark patch of the sky in the constellation Ursa Major and waiting patiently for photons that began their journey when our own planet was nothing but dust and gas. The first signals from 25 P-Nu-39 were unassuming, just a collection of pixels in a vast digital image, but it was Webb's specialized instruments that transformed this faint smudge into a cosmological crisis. The real revelation came not from the image itself, but from its spectrum. Using an instrument called the near-infrared spectrograph, or NIRSpec, astronomers performed a kind of cosmic autopsy on the galaxy's light. Spectroscopy is the science of breaking light down into its constituent colors. Its fundamental frequencies, much like a prism, separates sunlight into a rainbow. Every element, every atom in the universe, absorbs and emits light at specific, unique wavelengths. This creates a pattern of bright and dark lines in the spectrum, a kind of celestial barcode. This barcode is the astronomer's Rosetta Stone. It reveals a staggering amount of information: the object's chemical composition, its temperature, its density, and, most critically, its distance. As the team analyzed the barcode of 25 P-Nu-39, the first number they calculated was its redshift. The result was breathtaking. The lines in its spectrum were shifted so far toward the red end that it placed the galaxy at an era just 290 million years after the Big Bang. The universe at this point was less than 2% of its current age. This was the heart of the cosmic dark ages, a time when the first stars were just beginning to puncture the primordial hydrogen fog. To find any galaxy here was a triumph. But the subsequent data transformed triumph into sheer bewilderment. From the galaxy's brightness, the team could estimate its total stellar mass. The number that came back seemed like a computational error. 25 P-Nu-39 appeared to contain over 100 billion stars. It was a stellar metropolis, a galactic behemoth on par with our own Milky Way's spiral arm companions. This was utterly, unequivocally impossible according to our established models. Think of galaxy formation as a process of building with Lego bricks. The standard cosmological model says that in the early universe, you only have the smallest, most fundamental bricks available, tiny clumps of dark matter and gas. Over immense stretches of time, these small bricks slowly collide and merge, gravitationally attracting one another. Two small clumps form a slightly larger one. That larger one pulls in another, and so on. It is a slow, hierarchical process that unfolds over billions of years. First, you build small structures, then medium ones, then the grand, sprawling Lego castles like our Milky Way. What Webb had just found in 25P Nu 39 was a fully assembled, intricate Lego castle sitting in the box moments after it had been opened. There simply hadn't been enough time for it to be built, brick by agonizing brick. The paradox deepened with the analysis of its chemical composition. The spectral barcode showed strong signatures of elements like oxygen, nitrogen, and carbon. In astronomical parlance, anything heavier than hydrogen and helium is called a metal. But these metals are not created in the Big Bang. They are forged in the nuclear furnaces of stars and can only be released into the cosmos when those stars die in spectacular supernova explosions. To have such a significant abundance of these elements in a galaxy so young meant that it must have already gone through multiple generations of star birth and death. Massive, first-generation stars must have formed, burned through their fuel at a furious pace, exploded, and seeded the surrounding gas clouds with heavy elements. Then, a second generation of stars, rich in these new metals, must have formed from that enriched gas. This entire, frantic cycle of creation and destruction had to have occurred, at a rate and efficiency far beyond anything our simulations had ever suggested was possible. The galaxy was not only impossibly large, it was impossibly mature. It was chemically ancient at the dawn of time. The final piece of confounding evidence came from the imaging itself. While still a distant object, Webb's unparalleled resolution hinted at structure. It wasn't just a chaotic, disorganized clump of gas and stars, as one would expect from the violent early universe. There were suggestions of a central bulge, and perhaps even a nascent disk. It was organized. Gravity and angular momentum had already begun to shape it into a coherent, rotating system. This kind of organization takes time, eons of gravitational settling that 25P Nu 39 simply did not have. The evidence was overwhelming, and every new piece of data only sharpened the edges of the paradox. The team checked their calculations, they reran the models, they searched for any alternative explanation. Could it be a closer object masquerading as a distant one? The unambiguous redshift data made that impossible. Could the instrument be miscalibrated? All other objects in the same field of view behaved as expected. The inescapable conclusion was that 25P Nu 39 was real, and its existence posed a direct, profound challenge to our entire understanding of how the universe grew up. The standard model of cosmology, known as Lambda CDM, has been the bedrock of our cosmic understanding for decades. It is a remarkably successful framework that explains a vast range of observations, from the cosmic microwave background radiation to the large-scale distribution of galaxies. The lambda refers to dark energy, the mysterious force causing the accelerated expansion of the universe. The CDM stands for cold dark matter, an invisible, non-interactive substance that is believed to make up about 85% of all matter in the cosmos. In this model, it is the immense gravity of cold dark matter that provides the scaffolding for structure to form. After the Big Bang, the universe was almost perfectly smooth, but there were minuscule quantum fluctuations, tiny variations in density. Dark matter, being immune to the outward push of radiation pressure, began to clump together in the slightly denser regions. These clumps became the gravitational wells, the seeds into which ordinary matter, hydrogen and helium gas would later fall. This process is fundamentally bottom-up. The smallest dark matter halos form first, creating the gravitational cradles for the first dwarf galaxies. These dwarfs then merge over cosmic timescales, their stars and gas mixing, their central black holes combining, building up ever larger and more massive galaxies. Our own Milky Way is a testament to this history, a product of countless galactic mergers over 13 billion years, we can still see the shredded remnants of smaller galaxies it has cannibalized, long stellar streams that orbit our galactic core like ghosts of past victims. The Lambda CDM model has been tested and verified countless times. Its simulations, run on the world's most powerful supercomputers, produce a universe that looks remarkably like the one we observe around us today. But they do not, under any standard set of assumptions, produce anything like 25P nu 39. It is an outlier of such extreme proportions that it cannot be dismissed as a statistical fluke. The existence of this single, ancient object acts like a colossal wrecking ball, swung at the elegant edifice of hierarchical structure formation. It suggests that in the early universe, the process of building galaxies was not a slow, patient accumulation of small parts. Instead, it seems something allowed for massive, monolithic collapse. The universe, it appears, was capable of building its skyscrapers first. This single data point from the Webb telescope forces us to ask a terrifying and exhilarating question. Is our fundamental model of the cosmos wrong? Or, at the very least, is it woefully incomplete? When the initial paper on 25P nu 39 was published, the astronomical community was thrown into a state of vibrant turmoil. The first reaction, as is proper in science, was deep skepticism. Rival teams reanalyzed the public data, searching for flaws in the initial team's methodology. They looked for exotic explanations. Could there be some unknown foreground object whose light was being gravitationally lensed by an intervening galaxy cluster, making a small background object appear artificially large and bright? While lensing is a real phenomenon, the characteristics of 25P nu 39 didn't fit the profile. There was no telltale distortion or multiple imaging that lensing would produce. Gradually, as other early universe candidates with similarly challenging properties began to emerge, from other Webb deep field surveys, the skepticism began to shift toward a grudging acceptance. The data was real, the paradox was real, the crisis was here. This is not a moment of failure for science. On the contrary, it is the very essence of the scientific process. A theory is only as good as its ability to explain observations. When an observation emerges that fundamentally contradicts a theory, it is a gift, an opportunity to push beyond the boundaries of our knowledge and discover a deeper truth. 25P nu 39 has shattered the comfort of our established models and thrown open the doors to a new frontier of cosmic inquiry. The world's theorists are now scrambling, proposing bold and sometimes radical new ideas to explain how a galaxy could grow so big, so fast. One of the most compelling, if unsettling, ideas involves something called primordial black holes. Our standard model assumes the seeds of galaxies were tiny quantum fluctuations in density. But what if the universe was seeded with something much more substantial from the very beginning? Some theories suggest that in the chaotic, ultra-dense conditions of the first second after the Big Bang, regions of matter could have spontaneously collapsed under their own gravity to form black holes, not from dying stars, but directly from the fabric of space-time itself. These primordial black holes could have come in a range of sizes, some as massive as 100,000 suns. If they existed, they would have been phenomenal engines of galaxy formation. They would act as pre-existing, hyperdense anchors, their immense gravity immediately and rapidly pulling in vast reservoirs of gas from their surroundings. Instead of a slow, bottom-up process, this would be a get-rich-quick scheme for galaxy building. A massive primordial black hole could have seeded a behemoth like 25P nu 39, jump-starting its growth and allowing it to reach an impossible size in a cosmic blink of an eye. Webb may have inadvertently found the first circumstantial evidence for these long-theorized, elusive objects. Another avenue of investigation focuses on the universe's very first stars, the so-called population 3 stars. We have never directly seen these stars. They were born from pure hydrogen and helium and are thought to have been titans, hundreds of times more massive than our Sun. Because of their immense mass, they would have burned through their nuclear fuel with unimaginable ferocity living for only a few million years before exploding as colossal supernovae. Perhaps our models of these first stars are too conservative. What if they formed in much denser, more numerous clusters than we thought? What if their explosions were far more efficient at creating and distributing heavy elements? It's conceivable that a supercharged burst of population 3 star formation could have rapidly enriched and energized the gas in the early universe, allowing the next generation of stars, and thus the galaxy itself, to form at a pace that seems reckless by our current standards. 25P, Nu 39, might be the signature of this initial incredibly violent phase of cosmic creation, a process more akin to a wildfire than a slow smolder. A more fundamental revision might be needed in our understanding of the universe's most mysterious component, dark matter. We call it cold dark matter because we assume its particles move slowly, allowing them to clump together easily into the small halos that kickstart bottom-up formation. But what if it isn't so cold? Theories of warm or fuzzy dark matter propose particles that are lighter and move faster. These properties would suppress the formation of small-scale structures, favoring the collapse of much larger, more diffuse clouds of gas from the outset. This could naturally lead to the formation of massive galaxies first, a top-down scenario that would elegantly explain the existence of 25P Nu 39. Finding evidence that challenges the cold nature of dark matter would be a revolution, not just in cosmology, but in fundamental particle physics, opening a window into an entirely new sector of nature beyond the standard model. The James Webb Space Telescope was built for exactly this moment. It was designed not just to take pretty pictures, or to confirm what we already suspected to be true. Its primary mission, its deepest purpose, was to find the things that don't fit, to uncover the anomalies that break our theories. Because it is only at these breaking points, in these moments of profound confusion, that true progress is made. 25P Nu 39 is not an answer. It is a question, perhaps the most important question in cosmology today, and Webb is just getting started. As it stares deeper and for longer, it will find more of these impossible structures. It will map their distribution, study their stellar populations in greater detail, and provide the crucial data that will allow theorists to distinguish between these competing new ideas. We are standing on the cusp of a paradigm shift, a moment in history, akin to when Galileo first turned his telescope to the heavens and shattered the old geocentric model of the universe. The story of 25P Nu 39 is more than just a scientific puzzle. It is a profound lesson in cosmic humility. For centuries, we have crafted a story of the universe with ourselves as its thoughtful, intelligent observers. We built a model, Lambda CDM, that was neat, orderly, and predictive. We grew comfortable in our understanding of a slow, methodical cosmos. But the universe, it seems, is under no obligation to conform to our expectations or our timelines. It is wilder, more creative, and more complex than our models had allowed. It appears to have been in a furious hurry to build grand structures, to forge the elements of life, and to set the stage for the cosmic drama that would follow. This single, faint, red smudge from the dawn of time has forced us to reconsider our place in that story. It reminds us that our knowledge is a small island in a vast ocean of ignorance, and the purpose of science is not to forever defend the shores of that island, but to build ships and set sail into the unknown. The James Webb Space Telescope is our flagship, and it has just sent back a dispatch from a truly new world, one that operates by rules we are only just beginning to decipher. The impossible galaxy is a signpost, a beacon shining from the edge of time. It tells us that our neat and tidy origin story is about to be rewritten. The universe is stranger, more magnificent, and more surprising than we ever dared to imagine. And our quest to understand it, the greatest intellectual adventure in human history, has just entered a new and exhilarating chapter. The search continues. There is a map of everything that is, and it is a lie. Not a deliberate deception, but a lie born of perspective of our own infinitesimal place in the grand scheme. We have spent centuries charting the heavens, connecting the dots of light into constellations, then resolving those dots into suns, then those suns into islands of stars we call galaxies. Our instruments grew more powerful, our vision piercing deeper into the abyss of time and space, and with every leap in technology, the map grew denser, more intricate, more wonderfully, reassuringly full. You have seen this map in textbooks, in planetariums, on screens that pulse with simulated cosmic fly-throughs. It is a universe of breathtaking abundance. It shows us our own Milky Way, a swirling pinwheel of 100 billion suns as just one citizen in a local group of galaxies. This group in turn is a minor suburb of the Virgo supercluster, a sprawling metropolis of thousands of galaxies bound by their mutual gravitational pull. And even this colossal structure is but a single glittering thread in an even grander design. We call it the cosmic web. Imagine the entire observable universe as a single monumental living organism. The web is its nervous system, a luminous galaxy-encrusted scaffolding stretching across billions of light years. Gaseous filaments threaded with the invisible might of dark matter act as celestial highways, channeling rivers of galaxies towards immense gravitational basins. At the intersections of these filaments, you find the cosmic megacities, the superclusters, roaring with the light of 100,000 galaxies, each one a cauldron of star birth and stellar death. This is the universe we thought we knew. A cosmos where matter drawn by the irresistible siren song of gravity since the first moments after the Big Bang had dutifully clumped together. It is a universe of structure, of pattern, of celestial community. From the smallest dwarf galaxy to the most massive cluster, everything seemed connected, part of a coherent gravitationally woven tapestry. There were gaps, of course, smaller voids between the filaments, like quiet countrysides between the bright highways. These were expected. They were the natural result of gravity pulling matter away from some regions and into others. They were the gentle valleys in the cosmic landscape, necessary counterparts to the soaring mountain peaks of the clusters. This understanding was the bedrock of modern cosmology, a triumphant confirmation of our theories. The universe, while vast, was not random. It was organized. It was for the most part full. That was the beautiful, orderly, and profoundly misleading picture. To find the truth, we have to let go of our familiar signposts. We must abandon the comfort of the star-dusted filaments and the glowing galactic cities. We have to pull back, further, past the Virgo supercluster, leaving its billion-trillion suns behind until they merge into a single point of light. Further still past the Great Wall, a chain of galaxies stretching over 500 million light-years until it too becomes just a faint thread in the distance. We keep pulling back the scale of our journey, becoming almost nonsensical, the light-years piling up into the hundreds of millions. The intricate web of superclusters, once the largest thing we could imagine, now begins to resemble the foam on a wave, a delicate and fragile lattice against an ocean of something else. And it is here in this godlike perspective that the lie of our map is exposed. It is here that we see the wound, a place where the cosmic web isn't just thin, it has been torn asunder. A region where the filaments of creation themselves seem to have withered and died, where the great rivers of galaxies inexplicably detour, flowing around it, as if avoiding a place of cosmic plague. This is a region of space so vast, so desolate, so profoundly empty, it has no right to exist. We are looking at an anomaly that shatters our assumptions about how the universe is built. It is a hole in the fabric of the cosmos, a bubble of nothingness, inflated to a scale that defies our theories. Its name in the astronomical catalogues is unassuming clinical, the Butter's Void. But among those who study the largest structures of reality, it has earned a more fitting title, the Supergiant Void. The name is an understatement. If our Milky Way galaxy were to be placed at its very centre, our nearest galactic neighbour would be further away from us than we are from the Great Andromeda Galaxy many times over. To cross this chasm at the speed of light, the ultimate speed limit of the universe would take you 330 million years. Think of that. The dinosaurs rose, ruled the Earth for an epoch, and were wiped from existence, all in a fraction of the time it would take a single photon of light to traverse this one pocket of emptiness. A journey across it would be one of unimaginable loneliness. For millions of years, you would travel through a darkness deeper than any human has ever conceived. The familiar starry sky would vanish. The great river of the Milky Way, our galactic home, would shrink behind you until it was an indistinguishable smudge, then a single star, and then nothing. Looking forward, you would see only blackness, punctuated by the light of a few impossibly distant, lonely galaxies. The universe as you know it would cease to be. Inside this gravitational desert, the normal rules of cosmic real estate have been suspended. The average distance between galaxies in our neighbourhood is a few million light-years. Inside the supergiant void, it is tens of millions of light-years. Early surveys found almost nothing within its terrifying expanse, earning it the moniker the Great Nothing. More sensitive observations have since managed to identify a sparse handful of galaxies, perhaps 60 or so adrift in an ocean of space, that should by all rights contain thousands upon thousands. These are the loneliest galaxies in the universe. Castaways on a cosmic sea, they are like faint flickering lanterns separated by gulfs of darkness, so immense that their inhabitants, if any exist, would look up at a sky almost completely devoid of other galaxies. They would have no Andromeda to dream of reaching, no majestic superclusters painting their night with faint ghostly light. Their sky would be a testament to a profound, unnerving solitude, a universe that seems to have forgotten them. They exist as cosmic curiosities, statistical flukes that only deepen the central burning question. How did this happen? This is not just a geographical curiosity. The existence of the supergiant void is a direct monumental challenge to our fundamental understanding of the universe's evolution. The standard model of cosmology, our best and most tested explanation for everything we see, is built upon a simple and elegant premise. In the moments after the Big Bang, the universe was an almost perfectly smooth uniform soup of energy and matter. The seeds of all future structure were sown as microscopic quantum fluctuations, tiny variations in density from one point to another. Over 13.8 billion years, gravity acted on these seeds. The slightly denser regions pulled in more matter, becoming gravitational wells that would eventually blossom into the galaxies and clusters we see today. The slightly less dense regions were left behind, becoming the voids. The model works beautifully. It predicts the cosmic web, the size of clusters, the temperature of the background radiation, all with stunning accuracy. But it does not predict this. A void of this magnitude is a statistical monster. Our models can create voids certainly, but they are typically much smaller. To create a void, this colossal requires a seed of negative density in the early universe, an initial underdensity, so large and so empty that it stretches the limits of probability to the breaking point. It's like flipping a coin 1,000,000 times and having it land on heads every single time. It is so unlikely that it forces us to ask if the coin is rigged if the game itself is different from what we thought. The supergiant void suggests that there may be a piece missing from our cosmic puzzle, a force or a process that we have failed to account for. It stands as a silent, empty rebuke to our most cherished theories. It forces us to confront the possibility that the story of creation, the grand narrative from the Big Bang to today, might have a chapter we never knew existed, a chapter written in the language of absence. The implications are profound, reaching far beyond the sterile equations of physics. We humans are creatures of structure. We look to the heavens and find patterns, we chart the stars and feel connected to a larger whole. Our own galaxy, the Milky Way, resides on the edge of a smaller void, but we are firmly embedded within the luminous superstructures of the Laniakea supercluster. We live in a busy, well-lit cosmic suburb. We have neighbours. We are part of the Webb. The supergiant void shows us a different kind of cosmos. It is a glimpse into what the universe might have been. What if the initial quantum fluctuations had been different? What if the universe had been born with more such colossal underdensities? Our existence is predicated on being in the right place, a place where gravity had enough material to work with, to build stars, planets, and eventually us. But just next door, cosmically speaking, lies this abyss. It is a stark reminder that our bustling, star-filled corner of the universe is not the only possible outcome. Emptiness, it seems, is as fundamental to the cosmic architecture as fullness, perhaps even more so. What is this place? Is it merely an extreme statistical outlier, a one-in-a-trillion cosmic fluke that our theories must begrudgingly accommodate? Or is it something more? Is it the scar from an ancient, unimaginably violent cosmic event that literally blew a hole in the universe? Could it be evidence of a strange new property of dark energy, a force that is not only pushing the universe apart but is doing so unevenly, creating vast bubbles of accelerated expansion? Some have even whispered more exotic possibilities. Could such a void be the signature of an encounter with another universe, a bruise left on our cosmos from a collision in a higher dimension, an event that pushed all the matter out of this region forever? These are the questions that haunt the edges of modern cosmology, questions posed not by an abundance of evidence, but by a profound and terrifying lack of it. This is not just a story about what is out there, it is a detective story about what isn't. To understand the supergiant void is to embark on a journey into the heart of cosmic darkness, to decipher the meaning of absence on the largest scale imaginable. We must learn to read the clues left behind in the emptiness, for within this great silence the universe may be whispering its deepest secrets. What if the most important thing about the universe is not what's in it, but what isn't? For all our history, we have looked to the heavens and seen a spectacle of fullness, a celestial canvas saturated with light from the gentle glow of the Milky Way to the pinpoint diamonds of distant stars. We have defined our cosmos by its substance, by the glittering matter that populates the darkness. We assumed with a certainty bordering on faith that this substance was spread more or less evenly throughout the grand expanse, an elegant, predictable and profoundly reassuring idea. But what if hidden within that grand design, concealed by the very scale of the cosmos, there lay a wound, a region of such staggering, impossible emptiness that its discovery would not just add a new chapter to our understanding, but force us to tear out the very pages we thought were written in stone. This is the story of that discovery, a journey that began not with a search for nothing, but with humanity's oldest obsession, the desire to draw a map of everything. That primal urge to chart the unknown is woven into our very DNA. The first celestial cartographers were not astronomers in sterile observatories, but our distant ancestors huddled around fires tracing the movements of the gods and heroes they saw in the constellations. For them the sky was a familiar ceiling, a two-dimensional dome upon which the lights were hung. Their maps were not of space, but of myth and time. They marked the turning of the seasons, the paths for epic voyages, the divine clockwork that governed their lives. These charts were humanity's first great attempt to impose order on an overwhelming cosmos, to connect the glittering dots and transform a terrifying, chaotic wilderness into a comprehensible neighbourhood. For millennia, this was our universe, a single cosy sphere of stars with Earth at its heart. Even as our perspective shifted as we dethroned our own planet from the centre, the stars themselves remained a comforting backdrop, a fixed and beautiful tapestry against which the planets danced their elegant ballet. We learned the intricate mechanics of our solar system, but the great ocean of stars beyond remained just that, a beautiful but fundamentally flat decoration. The profound question of cosmic depth, of what lay between or beyond those lights, was a riddle for philosophers, not a problem for scientists. Then, at the dawn of the 20th century, our cosmic neighbourhood was shattered forever. The culprit was a new generation of colossal telescopes, glass eyes of unprecedented power, that began to resolve faint, fuzzy patches of light the ancients had called nebulae or clouds. A fierce debate ignited the astronomical community. Were these celestial smudges merely gas clouds within our own Milky Way galaxy, cosmic weather patterns close to home? Or were they something far more profound? Were they, as the philosopher Immanuel Kant had once speculated, island universes, entire galaxies like our own, adrift at unimaginable distances? The question struck at the very heart of our place in the universe. If they were nearby clouds, our Milky Way was the entirety of creation. But if they were distant galaxies, our home was but one island in a limitless archipelago, and the scale of reality had just expanded by a factor of millions. The debate raged for years, a scientific war of words waged over the interpretation of faint smudges on photographic plates. The answer, when it came, was delivered by a quiet, meticulous astronomer named Edwin Hubble, working at the Mount Wilson Observatory in California. In 1923, poring over a photographic plate of the Andromeda Nebula, Hubble identified a specific type of pulsating star, a Cepheid variable. These stars are cosmic lighthouses. Their intrinsic brightness is directly linked to the rhythm of their pulse, meaning that by measuring how fast they blink, you can calculate how bright they truly are. By comparing that true brightness to how dim they appear from Earth, you can calculate their distance with astonishing precision. It is the most fundamental yardstick in cosmology. When Hubble did the math for his star in Andromeda, the result was staggering. It was not thousands of light years away, nestled within our own galaxy. It was nearly 1 million light years distant, marooned in the intergalactic void, an island universe in its own right, perhaps even larger than our own Milky Way. In that single moment of calculation, the known universe inflated with explosive force. Our galaxy was not the whole story. It was a single sentence in a library of infinite volumes. This revelation launched a new era of cosmic exploration. Suddenly the mission was clear: to map this newly discovered cosmic ocean, to chart the locations of these countless new islands. For the next half-century, astronomers embarked on this grand cartographic project. With each new survey, the picture that emerged seemed to confirm a deep and satisfying intuition about the nature of reality. It was called the cosmological principle, a foundational idea which proposed that on the very largest scales, the universe is essentially the same everywhere. It is, in the language of physics, both homogeneous and isotropic. Think of it like looking at a vast, dense forest from an airplane. Down on the ground, you see a chaotic arrangement of individual trees, clearings and streams, but from 30,000 feet, all of that detail blurs into a uniform green carpet. The universe cosmologists believed was like that forest. Yes, there were clusters of galaxies, great gravitational cities of light, and there were less dense regions, the cosmic suburbs. But if you zoomed out far enough, this clumpiness would average out, revealing a smooth, consistent texture. The universe had no special center, no preferred edge, no strange anomalies. It was, in a statistical sense, orderly. This principle wasn't just an aesthetic preference. It was the bedrock upon which our most successful theories, including Einstein's general relativity, as applied to the whole cosmos, were built. Our models of the Big Bang and the subsequent evolution of the universe were all predicated on this assumption of large-scale uniformity. It was a universe that made sense, a cosmos whose structure, while immense, was ultimately predictable. The data seemed to agree. Photographic plates revealed a universe wallpapered with galaxies in every direction we looked. The story of the cosmos was the story of structure of matter clumping together under gravity to form stars, galaxies, and majestic clusters of galaxies. The idea of true profound emptiness on a colossal scale simply didn't fit. It had no place in the elegant equation of creation. By the late 1970s, however, a few astronomers began to feel that our two-dimensional maps were no longer sufficient. Simply taking pictures of the sky was like trying to understand the layout of a city by looking at a photograph taken from a single skyscraper. You could see the lights, but you had no sense of depth, no true understanding of the urban landscape's three-dimensional structure. To build a true map, you needed a third coordinate distance. And for this, astronomers turned to one of the strangest and most powerful phenomena in the universe: redshift. We've all experienced its auditory equivalent. When an ambulance siren screams past you, its pitch seems to rise as it approaches and then fall as it recedes. The sound waves are compressed as the source moves toward you and stretched as it moves away. Light behaves in exactly the same way. Thanks to Hubble's other monumental discovery, the expansion of the universe, we know that virtually every distant galaxy is moving away from us. The very fabric of space-time is stretching, and as it stretches, it pulls the light waves travelling through it, lengthening their wavelength. This stretching shifts the light towards the red end of the spectrum. It is a cosmic redshift. Crucially, the farther away a galaxy is, the faster it recedes, and the more its light is redshifted. Redshift, therefore, became the astronomer's ultimate surveying tool. It was no longer just a measure of velocity, it was a direct, reliable proxy for distance. By capturing the faint light from a galaxy and measuring its redshift, you could place it on a three-dimensional map. You could finally see the true architecture of the cosmos. In the early 1980s, a small, ambitious team of astronomers decided to undertake the most comprehensive survey of this kind ever attempted. Led by the sharp and driven Robert Kirshner at Harvard, the group included Augustus Umler, Paul Schechter, and a brilliant young postdoc named Stephen Schechtman. Their goal was to move beyond the flat photographic universe and create the first meaningful 3D slice of the cosmos. Their chosen method was painstaking, almost mind-numbingly repetitive. They would point the telescope at a specific patch of sky, focus on a single faint galaxy, and spend hours collecting its meagre photons. This light was then passed through a spectrograph which, like a prism, would break it down into its constituent colours, a rainbow barcode. Within that barcode, they would look for the characteristic spectral lines of known elements like hydrogen, and measure how far they had been shifted towards the red. Then they would move the telescope a fraction of a degree, and start the entire process over again on the next galaxy. It was slow, meticulous, grueling work, a form of celestial accounting performed during long cold nights at remote mountaintop observatories in Arizona and Chile. They were charting new territory, one galaxy at a time, extending a survey cone deep into the universe. Their expectation, guided by the cosmological principle, was clear. As they plotted their galaxies on their emerging 3D map, they anticipated seeing a relatively uniform spongy distribution of matter. They would find clusters, the dense knots where gravity had triumphed, and they would find regions with fewer galaxies, the voids that were expected to be part of this cosmic foam. But the overall pattern should be consistent. They were simply measuring the expected texture of the universe, confirming the standard model on a new, more precise scale. Their survey focused on several different wedges of the sky, thin slices of the universe designed to give them a representative sample of its structure. One of these wedges was pointed directly at the northern constellation of Bootes the Herdsman. As the data for this region began to accumulate, a deeply unsettling pattern, or rather a lack of one, started to emerge. They plotted the first galaxies, those closest to us, and they appeared right where expected. They plotted the next set a little further out, and the distribution still looked normal. But then, as they pushed deeper out to a distance of several 100 million light-years, something extraordinary happened. The galaxies just stopped. It wasn't a gradual thinning, a gentle transition from cosmic city to cosmic countryside. It was a wall. On their map, which should have been steadily populated with data points, there was suddenly nothing. A terrifying, gaping hole. At first their reaction was purely technical. Disbelief. The equipment must be faulty. Perhaps there was a flaw in the photographic plates used to select the target galaxies. Maybe the spectrograph was malfunctioning. Science demands skepticism, especially of its own results, when they seem to defy all logic. They checked their instruments. They recalibrated their detectors. They reviewed their methods from top to bottom, searching for some subtle, systematic error that could create such a phantom emptiness. There was none. The instruments were working perfectly. Their methodology was sound. The silence in their data was real. They pressed on, driven by a mixture of confusion and a dawning sense of awe. They kept surveying deeper into the Bootes wedge, pushing past the region of emptiness, hoping to see the familiar pattern of galaxies reappear on the other side. And eventually they did. Far beyond the void, hundreds of millions of light-years further on, the galaxies began to show up again, populating their map as if nothing were amiss. They had found the far wall of the emptiness. The team now faced an unavoidable and deeply disturbing conclusion. They had not found an error. They had stumbled upon a structure defined not by what it contained, but by its profound and haunting lack of substance. It was a bubble in the fabric of the cosmos, a spherical abyss of near-perfect nothingness. As they refined their measurements, the scale of their discovery became utterly mind-bending. This void, this hole in the universe, was nearly 330 million light-years across. It was so vast that if our own Milky Way galaxy were placed at its centre, we wouldn't have even known other galaxies existed until the 1960s. Thousands of galaxies based on the average density of the universe should have existed within that monumental volume. Their survey found only a handful scattered like lonely ships lost in an impossibly vast and silent ocean. The team had set out to map the predictable texture of the universe. Instead, they had found a monster, an anomaly so gargantuan it made a mockery of their models, a feature that the smooth uniform cosmos of the cosmological principle simply had no room for. This wasn't just a bigger-than-average clearing in the cosmic forest. This was the cosmic equivalent of finding a hole the size of North America in the middle of the Amazon rainforest. It was a statistical impossibility, a ghost of unimaginable proportions haunting the heavens. The Great Nothing, as it was sometimes called, was not just a new object to be catalogued. It was a profound challenge to everything we thought we knew, a terrifying question mark stamped across our map of reality. How could such a thing form? And if one such supergiant void existed, were there others hiding in the unmapped darkness? The search for answers was just beginning. That ghostly fingerprint left on the cradle of creation, the cold spot we saw imprinted on the universe's baby picture, was more than just a statistical curiosity. It was a whisper from the edge of time, a premonition. For years it remained just that an eerie, unexplained chill in the otherwise uniform warmth of the cosmic dawn. It was compelling yet frustratingly indirect, like finding a shadow without a source, or hearing a single discordant note in a perfect symphony. Theorists could spin elegant models suggesting exotic physics, parallel universes or textures in space-time itself. But to truly confront this enigma, to give it substance and form, we had to turn our gaze away from that ancient fading afterglow. We had to look directly into the darkness it pointed towards a patch of sky in the direction of the constellation Eridanus. We had to embark on a journey not back to the beginning of time, but deep into the fabric of the present-day universe. The challenge was monumental, a cartographer's nightmare. How do you map a three-dimensional space so vast that the light from its farthest shores has been travelling for hundreds of millions of years to reach you? A simple photograph, no matter how powerful the telescope, only gives you a flat two-dimensional projection. It's like looking at a dense forest from a distant mountaintop. You can see every tree, but you have no sense of depth. You cannot tell which tree is in the foreground and which stands miles behind it. To build a true map, to peel back the layers of the cosmos, astronomers needed a different kind of tool, a yardstick capable of measuring unimaginable distances. They found it not in a physical ruler, but in the very light of the stars. They found it in a phenomenon called redshift. Every galaxy, every star, every glowing cloud of gas in the cosmos sings a unique song written in the language of light. When you pass that light through a prism, a spectrograph, it breaks apart into a rainbow of colours, a spectrum. But this is no ordinary rainbow. It is tattooed with dark lines, specific frequencies of light that have been absorbed by the chemical elements within the galaxy. These lines are like a celestial barcode, a unique chemical signature for hydrogen, for helium, for oxygen, telling us what a galaxy is made of, yet they tell us something far more profound. We know from our models of the Big Bang, confirmed by decades of observation, that the universe is expanding everywhere and in all directions. Space-time itself is stretching, carrying galaxies along for the ride. As a galaxy rushes away from us, this very stretching of space also stretches the light waves travelling through it. Blue light is stretched towards the red end of the spectrum. Red light is stretched even further into the infrared. This stretching causes that entire celestial barcode, all those dark lines, to shift towards the red. The farther away a galaxy is, the faster it recedes from us, and the more dramatic this redshift becomes. This principle is the bedrock of modern cosmology. It is our cosmic depth gauge, our ultimate surveyor's tool. By meticulously measuring the precise redshift of a galaxy, we can translate its starlight into distance. We can transform a flat, beautiful image of the night sky into a staggering three-dimensional map of the cosmos. And it was with this tool that a handful of international teams set out to survey that cold, enigmatic patch of sky. They weren't just looking for one thing, they were aiming to count everything. Their goal was to conduct a slow-motion census of the heavens, one galaxy at a time. This was not a task for a single observer on a lonely mountaintop. It was an industrial-scale undertaking, a symphony of logistics and computation. Projects like the Sloan Digital Sky Survey, or SDSS, and the 2DF Galaxy Redshift Survey became the vanguard of this new era. These were not your grandfather's observatories. They were robotic mapping machines of breathtaking precision. Telescopes night after night would stare at a target patch of sky, but instead of a single camera, they used plates drilled with hundreds of holes, each one precisely aligned with the known position of a galaxy from a previous photographic survey. Into each hole, a fibre optic cable was plugged often by a meticulously programmed robotic arm. Each fibre would act like a tiny dedicated pipeline, siphoning the faint ancient light from a single distant galaxy, and feeding it into the hungry maw of a spectrograph. The machine could thus measure the redshifts of hundreds of galaxies simultaneously, a feat that would have taken a human astronomer decades to accomplish. For years, these surveys ran night after agonizingly clear night. The data streamed from the mountaintops in New Mexico and Australia to supercomputers across the globe. It was a relentless, painstaking process of accumulation. Each data point was a pinprick of light, a whisper from the void, a single coordinate in an impossibly large volume of space. For the scientists involved, it was an act of profound faith. They were assembling a puzzle with billions of pieces, most of which were still in the box. They spent their careers staring at screens filled with spectral lines, calibrating instruments against the subtle changes in Earth's atmosphere, writing complex algorithms to sift signal from noise. They were building point by point the most comprehensive map of the universe ever conceived. And as the map of that region around the cold spot began to take shape, something deeply strange and unsettling started to emerge. At first, it was a subtle statistical dip, a whisper in the data. The computer models which predict how galaxies should be distributed showed a smooth web-like structure. They predicted that within any given volume of space of this size, there should be a certain average number of galaxies. Think of it like a cosmic ocean filled with shimmering plankton. While the plankton might cluster together in some areas and be sparser in others, the overall density should be roughly consistent. But in the direction of Eridanus, the data was telling a different story. The count was consistently stubbornly low. It was as if their cosmic fishing net was coming up empty haul after haul. The initial reaction was one of professional skepticism. Perhaps there was a flaw in the instruments, a subtle error in the complex calibration software. Maybe a vast cloud of interstellar dust within our own Milky Way was obscuring the view, blocking the light from the galaxies behind it. They checked. They rechecked. They cross-referenced with different surveys, different telescopes, different teams on opposite sides of the planet. They analysed the data in infrared, which can pierce through dust, and the emptiness remained. The data was robust. The instruments were sound. The conclusion, however improbable, was becoming inescapable. Slowly, as more and more data points were added to the map, the true nature of the anomaly began to resolve itself. It wasn't a cloud of dust. It wasn't an instrument error. It was a hole in the universe. The pins on their three-dimensional map, each representing an entire galaxy, formed a magnificent glittering structure across billions of light years. They revealed the cosmic web in all its glory, long incandescent filaments of galaxies and dense compact clusters, where thousands of island universes swarmed together like bees in a hive. But right in the middle of their survey volume, this majestic structure simply stopped. The filaments frayed and vanished. The clusters gave way to an ocean of quiet. It was a region of profound and unsettling silence, a place where the symphony of cosmic structure had faded to black. As they defined its boundaries, the sheer scale of the thing became a source of both terror and awe. From one edge to the other, it measured over 250 million light-years. Let that number sink in for a moment. If you were to travel across it at the speed of light, the fastest anything can travel, your journey would take 330 million years. Our own Milky Way galaxy, with its hundreds of billions of stars, would be a barely visible speck of dust lost inside it. Our entire local group of galaxies, including Andromeda, would be an insignificant pebble in this colossal canyon. This was not just a void. This was a supergiant void. The largest, most empty space ever directly mapped by humankind. And the emptiness was almost absolute. Based on the standard models of cosmology, a volume of space this size should contain tens of thousands of galaxies, a rich and vibrant section of the cosmic web. The surveys, however, could only find a few dozen. A lonely handful of scattered, isolated galaxies like a few solitary blades of grass in a desert the size of a continent. The grand tapestry of the cosmos, it turned out, had a hole in it, a colossal wound in the fabric of reality itself. The confirmation sent a shockwave through the astronomical community. This wasn't some subtle deviation from a theoretical curve. This was a feature of the universe so enormous, so empty, that it felt like it shouldn't exist. It was like discovering a mountain range on Earth with a hole the size of North America bored straight through its centre. It simply didn't fit. The prevailing theories of galaxy formation, our best understanding of how the universe evolved from the smooth hot plasma of the Big Bang into the clumpy structured cosmos we see today, relied on the gentle persistent pull of gravity. Over billions of years, tiny fluctuations in density seeds of matter planted in the universe's first moments should have grown, pulling more and more matter together. Dark matter formed the invisible scaffolding, and normal matter, the stuff of stars and planets, and people settled into its gravitational wells, lighting up the cosmic web. This process is incredibly effective at building structures. It creates the filaments and the clusters we see everywhere, but it is notoriously bad at creating emptiness on this scale. How could you clear out a volume of space this large? What cosmic force could act as a celestial bulldozer, shoving tens of thousands of galaxies worth of matter out of a region, 1 billion light-years in circumference? The initial excitement of discovery quickly morphed into a state of profound scientific confusion. At conferences and in university halls, astronomers debated furiously. Some argued that it must still be a trick of the light and unknown systematic error that multiple teams had somehow missed. Others more boldly suggested that it was the first piece of evidence that our fundamental understanding of gravity itself might be incomplete. Our models were beautiful, they were powerful, they explained so much. But here was a monster staring back at us from the data, a structure so vast and so vacant that it defied those very models. It was a paradox written across the heavens. The ancient echo of the cold spot suggested this void was there and now. By mapping the galaxies directly, we had seen it with our own eyes. The shadow and the object casting it had finally been united. But in solving one mystery, we had uncovered a dozen more. This cosmic desert wasn't just an absence of matter, it was an absence of explanation. It represented a fundamental challenge to everything we thought we knew about how the universe built itself. We had discovered the largest structure in the known universe, and its defining characteristic was that nothing was there. The question was no longer simply what it was. The question, the one that would consume cosmologists for years to come, was why undefined? The confirmation hung in the air of observatories and university halls, a palpable silence that had replaced the initial shock. This was no longer a ghost in the data, no artifact of instrumentation, or a flaw in their calculations. The Botha's void was real, a chasm of cosmic proportions that stared back at humanity's most cherished theories and found them wanting. For the pioneers of modern cosmology, this was not a discovery to be celebrated, but a profound crisis to be confronted. Their maps of the universe, so carefully assembled from the faint light of distant galaxies, had suddenly revealed a flaw so monumental, so utterly incomprehensible, that it felt like finding an entire continent missing from a globe of the Earth. The Lambda dark matter model, the standard story of our cosmos, was the bedrock upon which their understanding was built. It described a universe born in fire, expanding and cooling, where the subtle quantum jitters of the infant cosmos were stretched by inflation into the seeds of all structure. Gravity, the patient and relentless sculptor, would then spend billions of years pulling matter together, weaving the luminous tapestry of the cosmic web. This model was elegant, powerful, and stunningly successful. It predicted the cosmic microwave background radiation with exquisite precision. It explained the formation of galaxies and the clustering of those galaxies into magnificent superclusters. It even accounted for the universe's accelerating expansion with a mysterious placeholder of dark energy. And yet it could not account for this. Supercomputer simulations, the digital universes born from the equations of this standard model, were run again and again, their parameters tweaked, and their initial conditions reset. They could create voids, certainly. Emptiness was a natural consequence of gravity's hoarding of matter. As filaments of dark matter pulled galaxies into great rivers and intersections of light, the spaces in between were expected to stretch and empty out like valleys deepening between rising mountain ranges. The models produced voids tens of millions of light-years across perhaps even 100 million in some extreme cases. But they never, not once, produced a monster of this magnitude. 330 million light-years. It was a statistical impossibility, an outlier so extreme it broke the bell curve of cosmic probability. To the theorists, it felt like running a simulation of Earth's weather and having it produce a hurricane the size of Asia. The model wasn't just slightly off, it was missing a fundamental piece of the puzzle, some unknown force or primordial condition that could excavate a region of space on a scale that defied imagination. The void became a theoretical battlefield. Did it point to a fatal flaw in our understanding of gravity itself? Perhaps on these immense scales, gravity behaved differently, becoming repulsive instead of attractive, actively pushing matter away. Such a heretical idea would require tearing down the pillars of both Newton and Einstein, a price few were willing to pay. Or maybe the problem lay in the universe's infancy. Could there have been a colossal underdensity in the primordial plasma, a cold spot, in the afterglow of the Big Bang, so vast that it was destined to become this supergiant void, a region starved of the seeds of structure from the very beginning? Such a thing would be a scar from creation itself, a feature that would challenge the very principle of a smooth and largely uniform early universe. The debates were fierce, the papers speculative, and the path forward shrouded in a thick intellectual fog. The void was more than an absence of galaxies. It had become an absence of answers, a gravitational well that was pulling in scientific certainty and leaving only questions in its wake. This was the dark night of the soul for observational cosmology. They had found the edge of a map that wasn't supposed to exist, and for a terrifying moment it seemed that all their compasses were spinning uselessly, pointing toward a profound and unnerving emptiness in their own knowledge. While the theorists wrestled with the ghost of this impossible structure, the observers, patient and methodical, decided to do the only thing they could. They decided to look closer. They returned to that patch of sky in the constellation Boötes the Herdsman, a region now synonymous with cosmic loneliness. But this time their goal was different. It was no longer about mapping the void's terrifying boundaries, but about staging an expedition into its heart. It was an act of profound observational defiance. The prevailing assumption was that there was nothing there to see a belief supported by years of initial surveys. Looking for a galaxy inside the Boötes void was like searching for a single grain of sand in a volume of space that could contain thousands of galaxies like our own Milky Way. It was a hunt for a needle in a haystack larger than a civilization could possibly comprehend. But science progresses not on assumption but on evidence, and the lack of evidence is not and never can be evidence of absence. So they pushed their instruments to the bleeding edge of their capabilities. Telescopes were tasked with staring into that abyss for hundreds of hours, accumulating photons one by one like collecting raindrops in a thimble during a drought. They were listening for the faintest whisper in a cathedral of silence. The work was painstaking, a slow and arduous process of sifting through immense data sets, filtering out the noise from distant quasars, the glare of foreground stars in our own galaxy, and the subtle imperfections of their own detectors. For months the results were the same. Nothing. Just the cold, featureless black, a seemingly endless confirmation of the void's utter emptiness. It was a test of faith in the scientific method itself, a relentless search for a single point of light in an ocean of darkness. And then it happened. Not with a sudden flash or a dramatic announcement, but with a quiet, methodical confirmation. Deep within the spectral data buried under layers of cosmic noise, a team meticulously cross-referencing photographic plates with new digital surveys found it. A faint, unassuming smudge. It was small, indistinct, and easily mistaken for an error, but the light from this smudge told an unambiguous story. It was redshifted to a degree that placed it squarely, undeniably inside the great nothing. It was a galaxy. It was a discovery that changed everything. The Boötes void was not, after all, completely empty. This first flicker of life was followed by another and then another. As survey techniques improved and telescopes became more sensitive, a sparse, lonely archipelago of galaxies began to resolve itself from the darkness. By the turn of the century, astronomers had catalogued a few dozen. These were not majestic spiral galaxies like our own Andromeda, nor were they colossal elliptical galaxies teeming with ancient stars. They were for the most part smaller, fainter, and strangely shaped. They were the survivors, the castaways, the lonely inhabitants of the cosmic desert. We call them void galaxies, and they are among the most isolated objects in the entire universe. Imagine for a moment what it would be like to stand on a planet in one of these galaxies. You would look up at a night sky of unimaginable blackness. Our own sky is rich with the faint collective glow of the Milky Way, a luminous band of billions of stars. We can see our neighbouring galaxies Andromeda and the Magellanic Clouds with the naked eye. But from a world inside a void galaxy, the sky would be terrifyingly barren. The nearest major galaxy would not be a mere 2.5 million light-years away as Andromeda is from us. It would be tens of millions, perhaps over 100 million light-years distant, an impossibly faint speck visible only to the most powerful telescopes. It would be a sky without neighbours, a sky that screams of solitude. You would live inside an island of light, a fragile raft of perhaps a few billion stars adrift in a sea of darkness so vast that the concept of intergalactic travel would seem like a cruel joke. The very nature of these galaxies tells a story of profound isolation. In the densely packed clusters of the cosmic Webb galaxies are constantly interacting. They collide, they merge, they strip gas and stars from one another in beautiful, violent gravitational dances. This cosmic rough and tumble is what forges new stars at a furious rate and sculpts galaxies into the familiar shapes we see today. But the void galaxies have been spared this drama. They have evolved in near-perfect quarantine, starved of the gas and dark matter that flows along the great cosmic filaments. As a result, they appear almost pristine like celestial fossils from an earlier, simpler epoch of the universe. Their star formation is often slower, their structures less defined. They are living laboratories for understanding what happens to a galaxy when it is left utterly, completely alone for billions of years. The revelation that the void was populated, however sparsely, was the crucial turning point in this entire cosmic mystery. It shifted the central question. It was no longer, why is there this giant hole, but rather, what process could create a hole this large while leaving a few survivors behind? The existence of these lonely islands of light provided the first tangible clues, the first handholds for theorists to begin climbing out of the intellectual abyss the void had created. And from this new perspective, two powerful and elegant hypotheses began to emerge, not as rivals, but as complementary parts of a grander solution. The first idea addressed the void's monstrous scale through a simple yet profound mechanism merger. We knew from our simulations that smaller voids should form naturally. What if, like soap bubbles in a sink, these smaller voids could drift together and coalesce over cosmic time? The theory suggested that the walls of these bubbles, the thin membranes of dark matter and galaxies separating them, could dissolve or be pushed aside, allowing smaller pockets of emptiness to merge into a single contiguous supervoid. This process would be driven by the subtle gravitational dynamics of the cosmic web itself. As the great superclusters, the colossal nodes of the web pull matter toward them with inescapable force, they don't just create voids, they also shepherd them. The spaces between the filaments would be squeezed and distorted, naturally pushing smaller voids into contact with one another. This hypothesis was beautiful in its simplicity. It didn't require any exotic new physics or a bizarre scarred infancy for the universe. It used the standard ingredients of cosmology, gravity, dark matter, and time, and showed how they could conspire to build a structure of such breathtaking emptiness. The few galaxies left behind would simply be the ones that happened to exist in the spaces that became the final void, the ones that were not swept away as the walls between the merging bubbles dissolved. They were the lucky few who were in the right place, or perhaps the wrong place when the great emptying took place. They were the evidence of the seams, the lingering remnants of the smaller structures that had been swallowed up to form the Leviathan. This elegant idea explained the how, but it was the second hypothesis that began to explain the why. This second idea forced an even more profound shift in our perspective, asking us to stop looking at the void as a thing in itself, and to see it instead as the consequence of something much, much larger. It asked us to zoom out to see the Bhuta's void not as a hole in the universe, but as a defining feature of its very architecture. This was the full embrace of the cosmic web. For decades, our maps of the universe had focused on the light on the galaxies on the matter. We were like explorers mapping a continent at night by charting the position of every campfire, every village, every city. The cosmic web was the network of roads and rivers connecting these points of light. But this new perspective demanded that we pay equal attention to the dark spaces between the lights. It argued that the voids were not anomalies. They were as fundamental to the structure of the universe as the filaments and clusters. They were the essential load-bearing negative space that gave the cosmic web its shape and strength. You cannot have the web without the voids. They are two sides of the same cosmic coin locked in a perpetual dance of gravity and expansion. The filaments are the skeletal bones of the cosmos, and the voids are the vast spaces within the skeleton that allow the structure to exist. To understand the universe, you had to understand its emptiness. This was the paradigm shift. The Buddha's void was transformed in our minds. It ceased to be a monster lurking in the dark, a freak of nature that broke our theories. It became instead the most extreme and magnificent example of a fundamental principle of cosmic organization. It was the grandest hall in the celestial palace, the widest valley in the cosmic landscape. Its sheer scale was no longer a problem to be solved, but a clue to be deciphered. A clue that pointed to the awesome power of gravity to organize matter over scales we can barely imagine. The two hypotheses together painted a new, richer picture. Over billions of years, the gravitational pull of the immense structures surrounding this region, the Hercules supercluster on one side, the Coma supercluster on another, had patiently herded matter into their domains. In the space between these growing cosmic empires, smaller voids began to form like puddles in drying mud. As the gravitational tides continued their work, these voids were pushed together, their boundaries dissolved, and they merged into the supergiant chasm we see today, leaving behind only a few lonely forgotten galaxies as witnesses to the process. The struggle was far from over, but the nature of the quest had changed. The terror of the unknown was being replaced by the thrill of a new kind of exploration. Scientists were no longer staring into an abyss of failed theories. They were looking at an integral piece of the cosmic puzzle, a piece that held profound secrets about the unseen universe. The void galaxies became our probes, their light carrying stories of their isolated existence. The void's boundaries became a laboratory for studying the delicate interplay between the immense gravitational pull of the filaments and the relentless outward push of dark energy that dominates the empty spaces. Suddenly, the great nothing was full of potential. It was a clean room for studying the universe in its purest form, a place where the fundamental forces of the cosmos could be observed on a grand stage unencumbered by the messy details of stars and gas. We had journeyed into the heart of darkness and discovered that it was not an ending, but a new beginning. We had found the key that could unlock a deeper understanding of the universe's grand design, forcing us to ask an even more profound question. If this is the architecture, what does it tell us about the architect? Faced with an anomaly that defies simple explanation, one that stares back from the cosmic dawn with a chilling indifference to our established theories, where do we even begin? The Eridanus. Supervoid is not merely a gap in the heavens. It is a profound chasm in our understanding, a direct challenge to the elegant architecture of the standard cosmological model. When direct observation presents such a paradox, we are forced to turn inward to recreate the universe itself. We must build it from the ground up, not with matter and energy, but with logic and mathematics inside the most powerful thinking machines ever conceived. We must run the clock back to the beginning of time, and let the cosmos evolve again and again, searching for a path, any path that leads to the colossal emptiness we see today. This is the realm of cosmological simulation, one of the most ambitious scientific endeavours ever undertaken. It is our attempt to forge a digital genesis. Inside the humming, water-cooled hearts of supercomputers, teams of astrophysicists become digital deities. They do not merely run a program, they instantiate a pocket universe. The process begins with a blank slate, a vast three-dimensional grid of virtual space empty of all substance. Into this digital void, scientists pour the ingredients of our cosmos as we know them. They add the precise amount of normal baryonic matter, the stuff of stars, planets, and ourselves, which accounts for a paltry 5% of the cosmic budget. They then add the dominant unseen components, 27% dark matter, and a staggering 68% dark energy. These are not just numbers, they are the fundamental parameters that dictate the universe's destiny. Next, they input the laws of physics, the non-negotiable rules of the game. Albert Einstein's theory of general relativity is the supreme code dictating how mass and energy warp spacetime, and how spacetime in turn tells matter how to move. With the ingredients and the rulebook in place, the final step is to provide the seed the initial conditions from which everything will grow. For this, they turn to the very echo of the Big Bang we explored earlier, the cosmic microwave background radiation. The faint temperature fluctuations in that ancient light, those minuscule variations of 1 part in 100,000, are digitized. They represent the primordial density differences in the infant universe, the slightly denser regions that would become the seeds of galaxies, and the slightly less dense regions that were destined to become voids. With the press of a key, 13.8 billion years of cosmic history are unleashed. Time compressed from eons into mere months of computational processing begins to flow. In the simulation's first moments, the universe is a nearly uniform hot dense soup. But gravity, relentless and patient, begins its work. The regions seeded with infinitesimally more dark matter begin to pull on their surroundings. These invisible gravitational anchors, this cosmic scaffolding, start to draw in the sparse hydrogen and helium gas of the early cosmos. The pull is gentle at first, an almost imperceptible cosmic tide. But over millions, then billions of years, the effect compounds. The rich get richer. Matter flows along invisible pathways, streaming from areas of lower density into areas of higher density, like rainfall carving channels, into a landscape forming rivulets, then streams, then mighty rivers. We can watch it happen. We can fly through these synthetic universes as they mature. We see the tendrils of gas and dark matter coalesce, twisting into vast luminous filaments. We witness the intersections of these filaments become bustling hubs of cosmic activity, blazing with the light of newborn stars and galaxies. These are the great galactic clusters, the glittering superhighways of the cosmic web. The simulation beautifully, breathtakingly recreates the large-scale structure of the universe that our telescopes reveal. It is a monumental triumph of theoretical physics and computational power, a testament to our ability to comprehend the cosmos on its grandest scale. The digital universe looks for all intents and purposes like our own. It has the same clumpy web-like texture, the same distribution of massive clusters, the same intricate network of filaments, and it has voids. The simulation naturally produces empty spaces. As matter is evacuated from the underdense regions and swept into the great cosmic rivers, vast deserts of near-nothingness are left behind. These digital voids grow their boundaries defined by the shimmering walls of the galactic filaments. They are an expected necessary feature of cosmic evolution. Yet here in this grand success lies the very heart of our problem. We run the simulations thousands of times, tweaking the initial conditions within the bounds of what the cosmic microwave background allows. We let them evolve, we watch them grow, we sift through petabytes of data representing galaxies that never were and stars that never shone. And in all of these attempts, in all of these carefully constructed digital realities, the standard model of cosmology fails to produce anything that comes close to the Eridanus supervoid. The simulated voids are numerous, but they are modest in scale. They are the natural consequence of gravity's organizing principle. The supergiant void, however, is a different beast entirely. It is not a pond, it is an ocean. Its sheer scale and its profound emptiness suggest that our digital recipe is missing a crucial ingredient, or perhaps that we have misunderstood the nature of the ingredients we are already using. The simulations, our most sophisticated tool for understanding the cosmos, are returning an impossible result. They are telling us in no uncertain terms that the void should not exist. This forces us to confront the bedrock of our model, starting with the universe's invisible architect, dark matter. For decades, our leading theory has been that dark matter is cold, meaning its constituent particles move slowly compared to the speed of light. This property is essential for the formation of galaxies. Slow-moving particles can clump together easily under their own gravity, forming the deep gravitational wells, or halos, that are necessary to trap ordinary matter and ignite star formation. In our simulations, this cold, dark matter acts as a magnificent gravitational shepherd, efficiently herding cosmic gas into the structures we see today. It is in many ways too efficient. Its powerful localized gravity is what builds the cosmic web, but it also resists the formation of truly enormous empty regions. The persistent gravitational pull of cold dark matter halos even from the edges of a void should prevent it from becoming as vast and empty as the Eridanus anomaly. The scaffolding is too strong, the gravitational anchors too heavy to permit such a colossal hole to be carved out of the cosmic structure. So what if our assumption is wrong? What if dark matter isn't entirely cold? Scientists have begun to experiment with warm or even hot dark matter models in their simulations. In these scenarios, the dark matter particles are lighter and move much faster. This has a dramatic effect on structure formation. Fast-moving particles can easily escape from smaller gravitational wells, effectively washing out or erasing the seeds for smaller structures like dwarf galaxies. This warm dark matter model has some appeal, as it might solve certain discrepancies between the predictions of cold dark matter and observations on smaller galactic scales. When applied to the problem of voids, the implications are tantalizing. A universe dominated by warmer dark matter would be smoother on small scales. Its gravitational scaffolding would be weaker, less sticky. Could such a universe more easily permit the formation of a supergiant void? The simulations provide a tentative but ultimately unsatisfying answer. While a warmer dark matter does indeed create a cosmos with fewer small galaxies and slightly larger voids, it still cannot fully account for the extreme nature of the Eridanus supervoid. Pushing the model to its limits, making the dark matter warm enough to even approach the required void size begins to create a new problem. It erases too much structure. The simulated universe no longer forms enough of the smaller galaxies we know exist. The model breaks in a different way. We seem to be trapped in a cosmic conundrum. The very component responsible for building the universe's structure, dark matter, seems incapable of allowing for its single largest area of unstructure. The architect cannot explain the empty hall. This impasse suggests we may be looking for the answer in the wrong place. We have been focused on gravity, the force that pulls things together. But what about the force that pushes things apart? This brings us to the most mysterious, most pervasive, and most powerful force in the entire universe, dark energy. First discovered in the late 1990s through observations of distant supernovae, dark energy is the name we give to the unknown influence that is causing the expansion of the universe to accelerate. For the first 7 billion years of cosmic history, gravity was winning the cosmic tug-of-war. The expansion initiated by the Big Bang was gradually slowing down, restrained by the mutual gravitational attraction of all the matter in the universe. But then something changed. A gentle, persistent, repulsive force, an intrinsic property of space-time itself, began to dominate. This is dark energy. It does not dilute as the universe expands. Instead, the more space there is, the more of this energy there is. It acts like a kind of anti-gravity, pushing everything away from everything else. It is a rising tide of space-time lifting all galaxies and carrying them away from each other at an ever-increasing speed. Now consider what such a force would do inside a region that was already from the very beginning slightly less dense than its surroundings. Imagine a primordial underdensity, one of the cool spots in the cosmic microwave background that was destined to become a void. In its youth, this region is still surrounded by matter, and the inward pull of gravity from the nascent filaments and clusters on its borders works to try and collapse it. But dark energy provides a counterpunch. Inside the void, where there is very little matter, and therefore very little gravity, the repulsive push of dark energy faces less opposition. On the outside, in the dense filaments, gravity is much stronger, and can temporarily overpower dark energy's influence. The result is a dynamic cosmic feedback loop. The matter on the edges of the void is pulled outward by the gravity of the massive superclusters, while simultaneously being pushed from behind by the accelerating expansion of space within the void itself. The void becomes an active agent in its own growth. It is not merely a passive emptiness left behind. It is an expanding bubble of space-time, a cosmic leaf blower actively scouring its own interior and driving matter away from its boundaries. When cosmologists incorporate this mechanism into their simulations, the results are startling. The voids are no longer static features. They become dynamic, evolving structures that grow significantly larger and emptier over the last half of the universe's history, precisely during the era when dark energy came to dominate. A small initial underdensity can be amplified, stretched and hollowed out by this relentless outward push. Dark energy, it seems, is the sculptor of emptiness. It takes the initial blueprint of density fluctuations laid down by the Big Bang and chiseled by the gravity of dark matter, and it carves out the great cathedrals of nothingness. This offers the most promising explanation we have for the existence of the Eridanus supervoid. It may be the result of a perfect cosmic storm, a region that started its life as one of the largest primordial underdensities, which was then mercilessly excavated over billions of years by the amplified effects of dark energy. And yet even this elegant solution opens a Pandora's box of new, more unsettling questions. The standard model, our Lambda CDM model, assumes that dark energy is a cosmological constant, meaning its density and repulsive strength are uniform everywhere in space and unchanging throughout time. It is a simple constant background hum to the universe. But the sheer scale of the Eridanus supervoid might be hinting that this simple picture is wrong. Could it be that dark energy is not constant? Is it possible that its effects are stronger inside this particular void than elsewhere in the cosmos? This is a radical paradigm-shifting idea. It suggests that the fundamental properties of the universe might vary from place to place. Perhaps the void is not just empty space. Perhaps it's a region where the nature of reality itself is subtly different. This leads to theories of dynamic dark energy or quintessence, where dark energy is a field that can fluctuate and evolve. In such a universe, the void might be a place where this field has a higher value, creating a localized pocket of super-accelerated expansion. The void would then be quite literally blowing itself up from the inside out. This also forces us to reconsider the relationship between the universe's two greatest mysteries. We have always treated dark matter and dark energy as separate, unrelated phenomena. One clumps, the other repels. One builds structure, the other drives expansion. But what if they are connected? Could there be some unknown interaction between them? Perhaps dark matter? Particles can decay or annihilate into dark energy. Or perhaps the presence of a strong dark energy field can alter the gravitational properties of dark matter. In the crucible of the supervoid, where matter is scarce, and dark energy's effects may be magnified, we could be seeing the signature of a new undiscovered physics that governs the dark sector of our universe. The cosmological simulations built to solve a puzzle have instead uncovered a deeper mystery. They have shown us that the interplay between gravity's pull and dark energy's push is far more complex and consequential than we ever imagined. The Eridanus supervoid is no longer just an anomaly. It has become a laboratory, a testing ground for the very limits of our knowledge. It forces us to ask, is the grand cosmic battle between matter and energy playing out differently in that vast darkness? And what does that imply about the ultimate fate of our universe as this strange repulsive energy continues its inexorable rise to absolute dominance? And so we were left suspended in a profound cosmic contradiction. A universe we thought we understood suddenly revealing an abyss that defied its own fundamental laws. The supergiant void was more than an anomaly. It was a ghost at the celestial banquet, an impossible emptiness that seemed to mock our models of a cosmos teeming with matter and energy. How could our theories of creation, which so beautifully described a universe born in fire and forged into a tapestry of brilliant galaxies, possibly account for such a colossal desert? The question echoed through the halls of astronomy, demanding an answer. Did we need to tear down our entire understanding of the universe and start again? Or was the key to this staggering emptiness hidden somewhere within the very theories it seemed to discredit? The truth, when it finally began to emerge, was more elegant and far more astonishing than we could have imagined. The void was not a monster that had come to tear our theories apart. It was in fact the ultimate proof that our theories were right all along. The resolution to this grand paradox has a name, a framework of mathematics and observation so robust it has become the bedrock of modern cosmology. It is called the Lambda Cold Dark Matter Model, or Lambda CDM. It is our standard model of the universe, a grand narrative that tells the story of everything from the first flicker of existence to the sprawling cosmic web we see today. You see, the answer to the void wasn't found by looking for a new exotic force that carved out the emptiness. It was found by realizing that the emptiness was an inevitable, and indeed essential, consequence of how everything else was built. Lambda CDM proposes that the universe is composed of three primary ingredients: the ordinary matter we know, the mysterious dark matter that provides the universe's gravitational scaffolding, and the enigmatic dark energy represented by the Greek letter lambda that drives the accelerating expansion of space itself. Within this cosmic recipe, the formation of voids is not an accident. It is a destiny written into the fabric of space-time from the very first moment of creation. To understand how we must journey back before the first star, before the first atom, to a time when the entire observable universe was compressed into a space smaller than a single grain of sand. Here in this embryonic cosmos, the laws of physics as we know them were just beginning to crystallize. The universe was an almost impossibly smooth and uniform sea of pure energy, a place of near-perfect equilibrium. But almost perfect is the crucial phrase. At the deepest, most fundamental level of reality, the quantum realm perfection is a fantasy. This primordial soup of energy was not placid. It was simmering with activity, a roiling foam of quantum fluctuations. Think of it as a constant, restless static, a cosmic hum beneath the silence. For infinitesimally brief moments, pairs of virtual particles would erupt into existence from absolutely nothing, only to annihilate each other a moment later, borrowing their brief existence from the energy of the void itself. These were not just random sparks in the dark. Each tiny fluctuation, each momentary hiccup in the energy field, represented a minuscule variation in density. One infinitesimally small patch of the universe would for a fleeting instant be slightly denser than the patch next to it. In our universe today, such quantum jitters are utterly inconsequential, their effects confined to the subatomic world. But in that first critical moment of cosmic history, the universe underwent a transformation so violent and so extreme, it would take these microscopic whispers and amplify them into a roar that would define the cosmos for all time. This event is called inflation. In a sliver of a second, a fraction of a heartbeat so small it defies human comprehension, the universe expanded exponentially. It didn't just grow, it detonated, swelling in size by a factor of at least a trillion. It was as if a single atom suddenly swelled to become larger than our entire Milky Way galaxy, all in less time than it takes for light to cross that same atom. This cataclysmic expansion did something extraordinary. It took those tiny ephemeral quantum fluctuations, those momentary ripples of higher and lower density, and it stretched them, locking them into the expanding fabric of spacetime itself. The microscopic variations that flickered in and out of existence were suddenly inflated to astronomical proportions. What was once a subatomic density difference became a region of space-light years across that was now fundamentally, permanently slightly denser than its surroundings. Conversely, the slightly less dense regions were stretched into vast expanses of slightly lower density. The quantum static of the universe's birth was instantly transformed into the blueprint for its entire future. These were the seeds of all structure. The slightly denser regions were the fertile ground where gravity would later plant the first galaxies, and the slightly less dense regions, they were the primordial seeds of the great voids. They were the empty basins waiting for the cosmic tide to recede. As the inferno of the Big Bang cooled, the fundamental forces of nature began to separate and take hold. The universe was still a hot, opaque plasma of particles, but now a new architect arrived on the scene: gravity. Gravity is patient, relentless, and democratic. It pulls on everything. However, it had a problem. The universe was still so hot and dense that photons, particles of a light, zipped around with incredible energy, creating an immense outward pressure. For the ordinary matter, the protons and neutrons that would one day form you, me, and the stars, this radiation pressure was like a constant violent wind, preventing it from collapsing together under gravity's pull. Any time a small clump of normal matter started to form, a blast of radiation would blow it apart. For millions of years, the creation of structure was locked in a cosmic stalemate. But this is where the second part of our model called dark matter takes center stage. We cannot see dark matter. It does not emit, reflect, or interact with light in any way. It is a ghost that passes through our world, through our very bodies, without leaving a trace. But it has mass, and therefore it has gravity. Crucially, because it is immune to the electromagnetic force, it was completely unaffected by that ferocious gale of radiation pressure that buffeted normal matter. While ordinary matter was being held in suspended animation, dark matter was free to obey gravity's call. In those primordial regions of slightly higher density, the stretched-out echoes of quantum fluctuations' dark matter began to clump together, Silently and visibly it started to coalesce, forming vast unseen halos, a ghostly cosmic skeleton. It was the first to fall into the gravitational well seeded by inflation, creating a hidden map of the future universe, a gravitational blueprint upon which everything else would be built. Then about 380,000 years after the Big Bang, the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms. This event, known as recombination, suddenly made the universe transparent. The photons were set free, that intense radiation pressure vanished, and for the first time ordinary matter was released from its prison. And what did it do? It immediately began to fall into the gravitational valleys that had already been carved out by the dark matter. For hundreds of thousands of years the dark matter had been building the scaffolding, and now the visible matter flowed in like concrete, settling into the framework that had been prepared for it. It was a cosmic migration on an unimaginable scale. Rivers of hydrogen and helium gas, trillions of miles long, streamed across the cosmos, drawn towards the immense invisible concentrations of dark matter. They flowed together, converging into ever denser sheets and long twisting filaments like water, finding its way through a complex network of channels. And this is the very process that created the voids. A void is not a bubble of nothing that was somehow inflated. It is not a hole punched in the universe by some cataclysmic event. A void exists because of what is not there. It is the natural, unavoidable consequence of gravity pulling matter somewhere else. The regions that began their life as those infinitesimally less dense quantum fluctuations now found themselves at a disadvantage. They had slightly less gravitational pull to start with. As the denser regions began to voraciously accrete matter, they didn't just gather material from their immediate vicinity. Their gravitational reach extended for millions of light years, actively pulling matter out of the less dense regions. It was a cosmic case of the rich getting richer and the poor getting poorer. The great filaments and walls of galaxies grew, becoming glittering superclusters, cities of light powered by billions of suns. And as they grew, the spaces in between were systematically emptied, evacuated by the relentless pull of these massive structures on their borders. The supergiant void, therefore, is not an anomaly. It is the ultimate expression of this process. It was born from one of the largest primordial underdensities, a vast quantum ripple stretched by inflation to an almost unbelievable size. For billions of years, the matter that once resided within its boundaries has been slowly, inexorably migrating outwards, drawn towards the gravitational embrace of the Hercules supercluster on one side and the Great Wall on the other. You can imagine it like a vast watershed. The filaments are the great rivers, and the superclusters are the oceans into which they flow. The voids are the enormous high-altitude deserts from which all the water has been drained away, leaving behind a profound and magnificent emptiness. They are the quiet, forgotten spaces between the cosmic highways, the dark continents on the map of the universe. They are a fundamental part of the cosmic ecosystem, their existence as necessary as the existence of the galaxies themselves. One cannot exist without the other. They are two sides of the same cosmic coin forged in the same quantum fire. The true triumph of the Lambda CDM model is not just that it provides a beautiful narrative explanation for this process. It's that it makes a concrete, testable prediction. Using the precise measurements of the universe's ingredients, the amount of dark energy, dark matter, and normal matter cosmologists can build virtual universes inside supercomputers. They can input the initial conditions observed in the cosmic microwave background radiation, the fossil light from the Big Bang, and then press play, allowing the simulation to evolve over 13.8 billion years according to the known laws of physics. And what do these simulations show? They show with breathtaking fidelity the emergence of a cosmic web. They show matter coalescing into filaments, nodes, and walls, and between them they show the formation of vast empty voids. The simulations don't just predict voids in general, they predict a distribution of voids of all sizes, from modest bubbles to truly colossal giants. When we run these simulations, we find that voids the size of the supergiant void, while rare are a statistically expected outcome of the Lambda CDM model. They are not cosmic freaks. They are the outliers, the grandest examples of a common phenomenon. Much like a 10,000-year flood is a rare but expected part of a planet's weather cycle. The void that once seemed to threaten our entire understanding of physics has transformed into one of its most powerful validations. It is a fossil record of the universe's infancy, its immense scale a direct physical remnant of a quantum fluctuation that existed in the first trillionth of a second of time. When you look at the emptiness, you're seeing the ghost of the quantum world magnified by inflation and sculpted by gravity into the largest coherent structure humanity has ever witnessed. The void is not a violation of the rules, it is a testament to their power and their reach across all of time and space. This revelation reshapes our entire perception of our cosmic home. We once imagined the universe as a sea of stars with islands of darkness. The reality is the precise opposite. The universe is an ocean of darkness, an interconnected network of voids and the galaxies, the stars, the planets, and we ourselves are merely the luminous foam clinging to the shores of this immense empty sea. The structure of the universe is not the galaxies but the emptiness itself. The void, once a symbol of our ignorance, has become a pristine laboratory. Because it is so empty, it is a place where the subtle, large-scale forces of the universe can be studied with unparalleled clarity. Within its depths, the gentle, persistent push of dark energy, the lambda in our model, is not drowned out by the noise of gravity from massive superclusters. The behaviour of the few lonely galaxies that drift through its expanse can tell us more about the ultimate fate of the universe than thousands of galaxies packed into a dense cluster. The mystery of the void's origin has been solved. The gaping hole in our cosmic map has been filled not with matter, but with understanding. We have traced its lineage back to the very dawn of time, revealing it to be a legitimate, if extraordinary, child of our universe's creation. The paradox has dissolved, replaced by a deeper appreciation for the intricate and often counterintuitive beauty of the cosmos. The supergiant void is no longer a source of cosmic dread, but a source of profound insight, a celestial classroom that confirms our most cherished theories about how everything came to be. But science is never static. The resolution of one great puzzle, always without fail, reveals another more subtle layer of questions lying just beneath. The puzzle of its existence was solved, but in its place new questions began to bloom. If the void is a perfect laboratory for testing cosmology, what secrets is it telling us now about the true nature of dark energy and the ultimate destiny of everything? What other whispers can we hear echoing across its silent, starless shores? And so we arrive at the end of our journey, back from the brink of the largest confirmed chasm in the known universe. We have travelled across billions of light years, not with starships, but with the penetrating light of distant galaxies and the patient gaze of our telescopes. We have peered into an abyss once thought to be a simple flaw, an anomaly in the cosmic census, only to discover that it is in fact an essential and profound feature of reality itself. The supergiant void, the immense emptiness we began by measuring, has ended by measuring us. It has tested the limits of our cosmological models, pushed the boundaries of our imagination, and fundamentally altered our dialogue with the cosmos. We began with a simple confounding observation, a patch of sky strangely barren, a gaping hole in the otherwise glittering tapestry of the universe. This was not the comfortable close-by vacuum between planets or stars, but a void of incomprehensible scale, a domain where thousands of galaxies should have been but were not. The initial sense of bewilderment felt by its discoverers was a feeling we have all now shared. It was a cosmic paradox, a question mark stamped across a billion light-years of space-time. What could possibly hollow out such a titanic volume of the universe? Was it the scar of some unknown violent cosmic event, or was it something else entirely, a clue to a deeper, more subtle architecture of existence? The answer, as we have seen, was not found in an act of cosmic violence, but in the quiet, persistent and cumulative whisper of gravity. We learned that the universe is not a uniform dispersal of matter, but a delicate frothing network of structure. On one side, the colossal filaments and superclusters, the luminous interstates of the cosmos where galaxies are drawn together into magnificent rivers of light, and on the other, the voids. These are not holes punched into the fabric of space, they are the spaces in between. They are the natural, inevitable consequence of gravity's grand project, the quiet backwaters that were simply left behind as matter flocked to more popular, denser neighbourhoods over the eons. The supergiant void is not an exception to the rule. It is the rule written in the largest letters we have ever seen. This realization marked a pivotal shift in our perspective. Emptiness was no longer a passive stage on which the cosmic drama unfolded. It became an active participant, a shaper of destiny. These voids are the cosmic watersheds, their subtle, gravitational divides dictating the flow of galaxies and the ultimate layout of the universe. They are the dark counterparts to the brilliant superclusters, two sides of the same cosmic coin. To understand the structure of one, you must understand the nature of the other. Our journey into the void was, in truth, a journey into the very heart of the cosmic web, revealing that the universe's story is written as much in its absences as in its presences. More profoundly, this immense region of underdensity became a unique laboratory for testing the most elusive forces in nature. We have travelled with photons of the cosmic microwave background radiation on their 13 billion year odyssey. We watched as they entered the void, their energy sapped by the climb out of the gravitational wells of surrounding superclusters. And then as they traversed the void's vast shallow basin, we saw the universe's accelerating expansion, driven by dark energy, stretch the very fabric of space beneath them. This stretching gave the photons a subtle, almost imperceptible boost of energy, a kick that warmed them ever so slightly. That minute temperature shift, the integrated Sachs-Wolf effect, is one of the most elegant and powerful pieces of evidence we have for the existence of dark energy. Think of it, the largest empty space we know became a cosmic magnifying glass, allowing us to see the subtle effects of the universe's dominant yet most mysterious component. Within its profound silence, the void amplified the whisper of dark energy into a signal we could finally detect. The absence of matter created the perfect conditions to study the force that is pushing all matter apart. It is a beautiful, staggering irony. The great nothing taught us more about the fundamental nature of everything than 1,000 galaxies crowded together ever could. It transformed from a mere curiosity into a cornerstone of modern cosmology, a silent testament to the unseen forces that govern our ultimate fate. The supergiant void is not just a place, it is a process. It is a dynamic, evolving entity. The faint, ghostly galaxies that still wander its lonely expanses are like isolated island universes, their evolution shaped by an extreme lack of interaction. They are cosmic hermits developing without the constant gravitational jostling and merging that defines life in the crowded galactic cities. Studying these isolated systems gives us a precious glimpse into how galaxies might have grown in a simpler, less chaotic universe. They are living fossils preserved in the sterile quiet of the void, holding clues to the fundamental processes of star formation and galactic assembly, stripped of all complicating factors. Furthermore, the void itself is growing. As the accelerating expansion of the universe continues, these vast basins of emptiness will deepen and expand. They will merge with one another, relentlessly pushing the great walls and filaments of galaxies further and further apart. In the unimaginably distant future, billions of years from now, an observer inside a galaxy like our own Milky Way might look out into the night sky and see nothing, absolutely nothing beyond their own local group of galaxies. The great cosmic web will have been stretched so thin that all other superclusters, all other filaments, all other signs of a grander structure will have accelerated beyond their cosmic horizon, their light no longer able to reach them. The universe will appear to them as a small isolated island of light in an infinite, eternal and truly empty void. They would have no evidence of the Big Bang, no hint of the cosmic web, no knowledge of the grand interconnected cosmos we are privileged to witness today. They would be trapped in a state of cosmic solitude. The voids in this sense are a chilling preview of our universe's ultimate fate, a future of increasing isolation and darkness, a final state of magnificent cold emptiness. Our ability to map the supergiant void and its brethren is a gift of our specific cosmic era, a window of opportunity that will one day close forever. This realization imbues our current exploration with a profound sense of urgency and privilege. We are the cosmic cartographers living in the golden age of cosmic discovery, and the map is still largely unwritten. The supergiant void, for all its immensity, is just one feature on a globe teeming with enigmatic continents and oceans. We have hinted at the Bootes Void, another colossal emptiness so stark it was nicknamed the Great Nothing. We have looked at the Eridanus supervoid, the potential source of the CMB cold spot, a puzzle that still fiercely divides the astronomical community. Is it merely a statistical fluke, or is it a sign of new physics, a brush with another universe? Perhaps each void is a new world to explore, each one a unique fossil, bearing the imprints of the universe's initial conditions. The precise shape size and emptiness of these voids are exquisitely sensitive to the parameters of our universe. The amount of dark matter, the nature of dark energy, the mass of neutrinos, and even the physics of the inflationary epoch moments after the Big Bang. The subtle variations in their structure are like geological strata holding the petrified history of cosmic evolution. By surveying them, by creating a comprehensive atlas of the cosmic underworld, we are performing a kind of cosmic archaeology on the grandest scale imaginable. And so we look to the future, to a new generation of explorers. The Vera C. Rubin Observatory in Chile will soon begin its legacy survey of space and time, a 10-year movie of the southern sky. It will map billions of galaxies, charting the cosmic web with unprecedented breadth and depth. The Euclid Space Telescope, a mission by the European Space Agency, is designed specifically to probe the geometry of the dark universe using the subtle distortions of distant galaxy images to map the distribution of both dark matter and the voids it helps to create. These instruments will not just find more voids, they will render them in stunning three-dimensional detail. They will turn our current impressionistic sketches into a photorealistic landscape. We will be able to walk through these cosmic canyons in virtual reality, to fly between the luminous filaments and into the heart of the deepest voids. We will measure their shapes, their connections, and their subtle gravitational imprints on space-time with a precision that was science fiction only a generation ago. We will compare these intricate real-world maps to our supercomputer simulations, testing our theories of cosmic origins to their breaking point. Will our standard model of cosmology hold, or will the detailed topography of these empty lands force us to rewrite our understanding of gravity of matter and of the universe's birth? The voids themselves hold the answer, waiting silently for us to ask the right questions. Our journey has taken us from a point of intellectual vertigo to a place of profound, if humbling, understanding. The universe is not just the glittering points of light, the stars, the nebulae, the galaxies. It is also the seemingly infinite darkness that connects them, the space that gives them shape and context. We are creatures of matter and light, naturally drawn to the bright and the dense. Our intuition struggles with the concept of a productive, meaningful emptiness. But the cosmos does not abide by our terrestrial intuitions. It operates on a scale where absence is as formative as presence, where the great voids are the very architects of the great walls. To truly comprehend our place in the cosmos, we must learn to see both. We must appreciate the intricate dance of the 100 billion galaxies in the Laniakea supercluster, and we must stand in awe of the silent, expansive majesty of the supergiant void. They are the yin and yang of creation, the opposing forces whose balance defines the reality we inhabit. We live on a tiny planet orbiting a single star tucked away in the suburbs of a fairly typical galaxy. But from this humble vantage point, we have reached out with our intellect and our instruments to chart the largest structures in existence. We have stared into the most profound abyss and found not a terrifying chaos, but a subtle, beautiful, and deeply informative order. The final lesson of the void is perhaps the most human one of all. It teaches us that looking into the darkness is not something to be feared. It is an act of discovery. It is in the quietest, most desolate corners of existence that some of the deepest truths are waiting to be found. The supergiant void, for all its emptiness, has filled our minds with wonder, with questions, and with a more complete, more honest picture of our cosmic home. A home that is at once astonishingly full and exquisitely empty, a universe of breathtaking complexity born from a simplicity we're only just beginning to grasp. And our quest to understand it, our journey as cosmic cartographers, has only just begun.